This video is about correlation analysis. We start by asking what a correlation analysis is. We will then look at the most important correlation analysis, Pearson Correlation, Spearman Correlation, Kendalls Tau and Point Biserial Correlation. And finally, we will discuss the difference between correlation and causation. Let's start with the first question. What is a correlation analysis? Correlation analysis is a statistical method used to measure the relationship between two variables. For example, is there a relationship between a person's salary and age? In this scatter plot, every single point is a person. In correlation analysis, we usually want to know two things. Number one, how strong the correlation is. And number two, in which direction the correlation goes. We can read both in the correlation coefficient, which is between -1 and 1. The strength of the correlation can be read in a table. If R is between 0 and 0.1, we speak of no correlation. If R is between 0.7 and 1, we speak of a very strong correlation. A positive correlation exists when high values of one variable go along with high values of the other variable, or when small values of one variable go along with small values of the other variable. A positive correlation is found, for example, for body size and shoe size. The result is a positive correlation coefficient. A negative correlation exists when high values of one variable go along with low values of the other variable, and vice versa. A negative correlation usually exists between product price and sales volume. The result is a negative correlation coefficient. Now we have different correlation coefficients. The most popular are Pearson Correlation Coefficient R, Spearman Correlation Coefficient RS, Kendalls Tau, and Point Biserial Correlation Coefficient RPB. Let's start with the first, the Pearson Correlation Coefficient. What is a Pearson correlation? As all correlation coefficients, the Pearson correlation R is a statistical measure that quantifies the relationship between two variables. In the case of Pearson correlation, the linear relationship of metric variables is measured. More about metric variables later. So with the help of Pearson correlation, we can measure the linear relationship between two variables. And of course, the Pearson correlation coefficient R tells us how strong the correlation is and in which direction the correlation goes. How is Pearson correlation calculated? The Pearson correlation coefficient is obtained via this equation, where R is the Pearson correlation coefficient, xi are the individual values of one variable, for example age, yi are the individual values of the other variable, for example salary, x dash and y dash are respectively the mean values of the two variables. In the equation, we can see that the respective mean value is first subtracted from both values. So in our example, we calculate the mean values of age and salary. We then subtract the mean values from each person's age and salary. Then we multiply both values and we sum up the individual results of the multiplication. The expression in the denominator ensures that the correlation coefficient is scaled between -1 and 1. If we now multiply two positive values, we get a positive value. So all values that lie in this area have a positive influence on the correlation coefficient. If we multiply two negative values, we also get a positive value. Minus times minus is plus. So all values that lie in this area also have a positive influence on the correlation coefficient. If we multiply a positive value and a negative value, we get a negative value. Minus times plus is minus. So all values that lie in these ranges have a negative influence on the correlation coefficient. Therefore, if our values are predominantly in these two areas, we get a positive correlation coefficient, and thus a positive relationship. If our values are predominantly in these two areas, we get a negative correlation coefficient, and thus a negative relationship. If the points are distributed over all four areas, the positive terms and the negative terms cancel each other out, and we get a very small or no correlation. But now there's one more thing to consider. The correlation coefficient is usually calculated with data taken from a sample. However, we often want to test a hypothesis about the population. In the case of correlation analysis, we then want to know if there is a correlation in the population. For this, we check whether the correlation coefficient in the sample is statistically significantly different from zero. The null hypothesis in the Pearson correlation is the correlation coefficient does not differ significantly from zero. There is no linear relationship. And the alternative hypothesis is the correlation coefficient differs significantly from zero. There is a linear relationship. Attention! It is always tested whether the null hypothesis is rejected or not. In our example, the research question is there a correlation between age and salary in the British population? To find out, we draw a sample and test whether in this sample the correlation coefficient is significantly different from zero. The null hypothesis then is there is no correlation between salary and age in the British population. And the alternative hypothesis, there is a correlation between salary and age in the British population. Whether the correlation coefficient is significantly different from zero based on the sample collected can be checked using a t-test, where R is the correlation coefficient and N is the sample size. A p-value can then be calculated from the test statistic t. If the p-value is smaller than the specified significance level, which is usually 5%, then the null hypothesis is rejected, otherwise it is not. But what about the assumptions for a Pearson correlation? Here we must distinguish whether we just want to calculate the Pearson correlation or whether we want to test a hypothesis. To calculate the Pearson correlation coefficient, only two metric variables need to be present. Metric variables are, for example, a person's weight, a person's salary, or electricity consumption. The Pearson correlation coefficient then tells us how large the linear relationship is. If there is a non-linear relationship, we cannot tell from the Pearson correlation coefficient. However, if we want to test whether the Pearson correlation coefficient is significantly different from zero, the two variables must always be normally distributed. If this is not given, the calculated test statistic t or the p-value cannot be interpreted reliably. Let's continue with the Spearman correlation. The Spearman rank correlation is the non-parametric counterpart of the Pearson correlation. But there is an important difference between both correlation coefficients. Spearman correlation does not use the raw data, but the ranks of the data. Let's look at this with an example. We measure the reaction time of 8 computer players and ask their age. When we calculate a Pearson correlation, we simply take the two variables reaction time and age and calculate the Pearson correlation coefficient. However, we now want to calculate the Spearman rank correlation. So first we assign a rank to each person for reaction time and age. The reaction time is already sorted by size. 12 is the smallest value, so gets rank 1. 15, the second smallest value, so gets rank 2, and so on and so forth. We are now doing the same with age. Here we have the smallest value, there the second smallest, there the third smallest, fourth smallest, and so on and so forth. Let's take a look at this in the scatter plot. Here we see the raw data of age and reaction time. But now we would like to use the rankings. So we form ranks from the variables age and reaction time. Through this transformation, we have now distributed the data more evenly. To calculate the Pearson correlation, we simply calculate the Pearson correlation from the ranks. So the Spearman correlation is equal to the Pearson correlation, only that the ranks are used instead of the raw values. Let's have a quick look at that in Data tab. Here we have the reaction time and age, and there we have the just created ranks of reaction time and age. Now we can either calculate Spearman correlation of reaction time and age, where we get a correlation of 0.9. Or we can calculate Pearson correlation from the ranks, where we also get 0.9, so exactly the same as before. If you like, you can download the dataset. You can find the link in the video description. If there are no rank ties, we can also use this equation to calculate the Pearson correlation. RS is the Spearman correlation, N is the number of cases, and D is the difference in ranks between the two variables. Referring to our example, we get the different D's with this. 1 minus 1 is equal to 0, 2 minus 3 is minus 1, 3 minus 2 is 1, and so on. Now we square the individual D's and add them all up. So the sum of Di squared is 8. N, which is the number of people, is 8. If you put everything in, we get a correlation coefficient of 0.9. Just like the Pearson correlation coefficient R, Spearman correlation coefficient RS also varies between -1 and 1. Let's continue with Kendalls Tau. Kendalls Tau is a correlation coefficient and is thus a measure of the relationship between two variables. But what is the difference between Pearson correlation and Kendall's rank correlation? In contrast to Pearson correlation, Kendall's rank correlation is a non-parametric test procedure. Thus, for the calculation of Kendalls Tau, the data need not be normally distributed and the variables need only have ordinal scale levels. Exactly the same is true for the Spearman rank correlation, right? That's right! Kendalls Tau is very similar to Spearman's rank correlation coefficient. However, Kendalls Tau should be preferred over Spearman's correlation if very few data with many rank ties are available. But how is Kendalls Tau calculated? We can calculate Kendalls Tau with this formula, where C is the number of concordant pairs and D is the number of discordant pairs. What are concordant and discordant pairs? We will now go through this with an example. Suppose two doctors are asked to rank 6 patients according to their physical health. One of the two doctors is now defined as a reference and the patients are sorted from 1 to 6. Now the sorted ranks are matched with the ranks of the other doctor. E.g., the patient who is in 3rd place with the reference doctor is in 4th place with the other doctor. Now, using Kendalls Tau, we want to know if there is a correlation between the two rankings. For the calculation of Kendalls Tau, we only need these ranks. We now look at each individual rank and note whether the values below are smaller or greater than itself. So we start at the first rank 3. 1 is smaller than 3, so gets a minus. 4 is greater, so gets a plus. 2 is smaller, so it gets a minus. 6 is greater, so it gets a plus. And 5 is also greater, so it also gets a plus. Now we do the same for 1. Here, of course, each subsequent rank is greater than 1. So we have a plus everywhere. At rank 4, 2 is smaller and 6 and 5 are greater. Now we do this for rank 2 and rank 6. Then we can easily calculate the number of concordant and discordant pairs. We get the number of concordant pairs by counting all the plus. In our example, we have 11 plus in total. We get the number of discordant pairs by counting through all the minus. In our example, we have a total of 4 minus. C is thus 11 and D is 4. Kendalls Tau now is 11 minus 4 divided by 11 plus 4. And we get a Kendalls Tau of 0.47. We get an alternative formula for Kendalls Tau herewith. S is C minus D, therefore 7. N is the number of cases, i.e. 6. If we insert everything, we also get 7 divided by 15. Just like the Pearson correlation coefficient R, Kendalls Tau also varies between -1 and +1. We have again calculated the correlation coefficient using data from a sample. Now we can test if the correlation coefficient is significantly different from 0. Thus, the null hypothesis is the correlation coefficient tau is equal to 0, there is no relationship. And the alternative hypothesis is the correlation coefficient tau is unequal to 0, there is a relationship. Therefore, we want to know if the correlation coefficient is significantly different from 0. You can analyze this either by hand or with a software like DataTab. For the calculation by hand, we can use the set distribution as an approximation. However, for this we should at least have 40 cases, so the 6 cases from our example are actually too few. We get the set value with this formula. Here we have tau, and n is the number of cases. This brings us to the last correlation analysis, the point biserial correlation. Point biserial correlation is a special case of Pearson correlation and examines the relationship between a dichotomous variable and a metric variable. What is a dichotomous variable and what is a metric variable? A dichotomous variable is a variable with 2 values, for example, gender with male and female, or smoking status with smoker and non-smoker. A metric variable is, for example, the weight of a person, the salary of a person, or the electricity consumption. So, if we have a dichotomous variable and a metric variable, and we want to know if there is a relationship, we can use a point biserial correlation. Of course, we need to check the assumptions beforehand, but more about that later. How is the point biserial correlation calculated? As stated at the beginning, the point biserial correlation is a special case of the Pearson correlation. But how can we calculate the Pearson correlation when a variable is nominal? Let's look at this with an example. Let's say we are interested in investigating the relationship between the number of hours studied for a test and the test result, passed, failed. We've calculated data from a sample of 20 students, where 12 students passed the test and 8 students failed. We have recorded the number of hours each student studied for the test. To calculate the point biserial correlation, we first need to convert the test result into numbers. We can assign a score of 1 to students who passed the test and a score of 0 to students who failed the test. Now we can either calculate the Pearson correlation of time and test result, or we use the equation for the point biserial correlation. x1 dash is the mean value of the people who have passed, and x2 dash is the mean value of the people who failed. n1 is the number of people who passed, and n2 the number of people who failed, and n is the total number. But whether we calculate the Pearson correlation or we use the equation for the point biserial correlation, we get the same result both times. Let's take a quick look at this in DataTab. Here we have the learning hours, the test result with passed and failed, and there the test result with 0 and 1. We define the test result with 0 and 1 as metric. If we now go to correlation and calculate the Pearson correlation for these 2 variables, we get a correlation coefficient of 0.31. If we calculate the point biserial correlation for learning hours and exam result with passed and failed, we also get a correlation of 0.31. Just like the Pearson correlation coefficient R, the point biserial correlation coefficient RPB also varies between -1 and 1. If we have a coefficient between -1 and less than 1, there is a negative correlation, thus a negative relationship between the variables. If we have a coefficient between greater than 0 and 1, there is a positive correlation, that is, a positive relationship between the two variables. If the result is 0, we have no correlation. As always, with the point biserial correlation, we can also check whether the correlation coefficient is significantly different from 0. Thus, the null hypothesis is the correlation coefficient R is equal to 0, there is no relationship, and the alternative hypothesis is the correlation coefficient R is unequal to 0, there is a relationship. Before we get to the assumptions, here's an interesting note. When we compute a point biserial correlation, we get the same p-value as when we compute a t-test for independent samples for the same data. So, whether we test a correlation hypothesis with the point biserial correlation or a difference hypothesis with the t-test, we get the same p-value. Now, if we compute a t-test in datatype with these data and we have the null hypothesis, there is no difference between the groups failed and passed in terms of the variable learning hours, we get a p-value of 0.179. And also, if we calculate a point biserial correlation and have the null hypothesis, there is no correlation between learning hours and test result, we get a p-value of 0.179. In our example, the p-value is greater than 0.05, which is most often used as a significance level, and thus the null hypothesis is not rejected. But what about the assumptions for a point biserial correlation? Here we must distinguish whether we just want to calculate the correlation coefficient or whether we want to test a hypothesis. To calculate the correlation coefficient, only one metric variable and one dichotomous variable must be present. However, if we want to test whether the correlation coefficient is significantly different from 0, the one metric variable must also be normally distributed. If this is not given, the calculated test statistic t, or the p-value, cannot be interpreted reliably. This brings us to the last question. What is causality? And what is the difference between causality and correlation? Causality is the relationship between a cause and an effect. In a causal relationship, we have a cause and a resultant effect. An example: coffee contains caffeine, a stimulating substance. When you drink coffee, the caffeine enters the body, affects the central nervous system, and leads to increased alertedness. Drinking coffee is the cause of the feeling of alertedness that comes afterwards. Without drinking coffee, the effect, i.e. the feeling of alertedness, would not occur. But causality is not always so easy to determine. Clear requirements must be met in order to speak of a causal relationship. But more about that later. So, what is the difference between correlation and causality? A correlation tells us that there is a relationship between two variables. Example: there is a positive correlation between ice cream sales and the number of sunburns. However, an existing correlation cannot tell us which variable influences which, or whether a third variable is responsible for the correlation. In our example, both variables are influenced by a common cause, namely sunny weather. On sunny days, people buy more ice cream and spend more time outdoors. This can lead to an increased risk of sunburns. Causality means that there is a clear cause-effect relationship between two variables. Causality exists when you can say with certainty which variable influences which. However, a common mistake in the interpretation of statistics is that a correlation is immediately assumed to be a causal relationship. Here is an example. The American statistician Darrell Huff found a negative correlation between the number of head lice and the body temperature of the inhabitants of an island. A negative correlation means that people with many head lice generally have a lower body temperature, and people with few head lice generally have a higher body temperature. The islanders concluded that head lice were good for health because they reduced fever. So their assumption was that head lice have an effect on the temperature of the body. In reality, the correct conclusion is the other way around. In an experiment, it was possible to prove that high fever drives away the lice. So the high body temperature is the cause, not the effect. What are the conditions for talking about causality? There are two conditions for causality. Number one, there is a significant correlation between the variables. This is easy to check. We simply check whether the correlation coefficient is significantly different from 0. Number two, the second condition can be met in 3 ways. First, chronological sequence. There is a chronological sequence and the results of one variable occurred before the results of the other variable. Second, experiment. A controlled experiment was conducted in which the two variables can be specifically influenced. And number 3, theory. There is a well-founded and plausible theory in which direction the causal relationship goes. If there is only a significant correlation, but none of the other 3 conditions are met, we can only speak of correlation, never of causality. Thanks for watching, and I hope you enjoyed the video.